Hello, this is Jack Jackson. I want to introduce to you this hyperbolic half-plane geometry environment that I've created. Um, this is the app here, and you can see down below there is a little bit of text down there. Okay, but to work this, you're going to want to go up here to these three dots in the upper corner, click on that, and say Open in the app. Okay, so now when you do this, you have access to new tools. So hyperbolic geometry is a type of non-Euclidean geometry, and there are actually multiple models for this that can be embedded in Euclidean geometry. There's a disk model. There's some 3D models, and then there's also this model here that I'm going to use, which is the Beltrami-Poincare Half-plane model. And in this model, the points are in this white area, which is all the ones with positive coordinates. You have a horizontal edge to the half plane, which is the x-axis, and the stuff down here below the x-axis with negative y coordinates are not part of the plane. So the plane is only this open half plane up here. So we can think of these. This is the half-plane edge here as being points at infinity, and my students say, well, this is to infinity and beyond, so maybe Buzz Lightyear might be down here, but there are no points of the geometry down there. Okay, so what I've done is I've created tools here that are very similar to the tools that you're used to in regular Euclidean geometry in GeoGebra, but they are for hyperbolic objects. So these two and this first toolbar are the same as normal. This one's almost the same, except you have a hyperbolic version of the midpoint instead of the Euclidean version. This is for doing things with straight objects, which are not Euclidean straight, but hyperbolic straight, things like lines, rays, line segments, parts of lines. This is some special lines, perpendiculars. This has to do with circles. This one has to do with angles. This one has to do with measuring distance and some transformations. These are normal. And then this last one over here is all the Euclidean tools have been collected over here just in case you need them. Although these are not actually correct objects in hyperbolic, those tools are still available if you'd like to use them. Okay. So be sure when you're putting points, you don't put any points on the edge or down here. They can be moved down there. When things go down there, things mess up. So first thing is, what does a line look like? Well, just as in Euclidean geometry, 2 points determine a line. So given any 2 points, there's exactly one line containing those 2 points. And, well, that's different. That's what the line looks like in hyperbolic geometry. Hyperbolic geometry actually has all the postulates of Euclidean geometry except for the parallel postulate, and I'll show you why, how it violates the normal Euclidean parallel postulate here in just a minute. But this is a line. It's the normal kind of line is a Euclidean semicircle with the center of the circle down here on the edge, and the endpoints of the semicircle on the edge, and of course those endpoints, any point on the edge is not included. Now there's actually 2 types of lines, and this actually produces both of them. If you can ever get this to have exactly the same x coordinates, then what happens now, it's no longer a Euclidean semicircle, it's a Euclidean open ray, open endpoint on the circle, on the edge, and then going up vertically. Okay, now because of this dual nature of lines, I've got it set up so that both will be created here either way, but they're actually, in GeoGebra, there are 2 different objects. They're both created by this one tool, but that can give you some little bit of hassles when you use this in creating other things. So there's a line. Here's a ray, which of course is just half a line, just like it is in Euclidean geometry. So it'll be half of be a part of a semicircle here, or it could be a ray going straight up. So it would actually be a Euclidean ray. Or if it's straight down this way, it'll be a Euclidean line segment with an open endpoint on the edge. Or normally it's an arc of a circle, like that, portion of a semicircle. So all of those are Euclidean, all of those are hyperbolic rays, and those are created here. Of course, a hyperbolic line segment is a continuous piece of a line. So it's going to be, Euclidean wise, it's going to be an arc of a circle, or it's going to be a vertical line segment. Okay, and so it is the path of shortest distance from one point to the other, just like in Euclidean geometry. Now, one of the big differences, of course, is how distance is measured here. Okay, so we'll get back to that. Actually, I could tell you, we'll go over that maybe in another video, but distance is measured differently. And so that if you're going from this point all the way to the edge, that's infinitely long, the way the distance is measured. Okay, so you can think of the edge as being points at infinity. Okay, so those are some of the basic things you can do with this here. Let's go back to building a line segment. Under the original thing here, you have your normal things about points on an object and attach and detach points and finding intersections. But here we have a hyperbolic midpoint. It's going to be, between those two endpoints on the line segment, but it's not the Euclidean midpoint of that line segment normally. So you can clearly see that it might be closer to one end than the other as measured by Euclidean distance, but as far as hyperbolic distance, it's the same distance from here to here. So speaking of hyperbolic distance, let's go over to here and actually measure it. And so there, the distance between those 2 points is there. Now, by the way, when you do some things, sometimes when you click on these things and ask it for a measurement, measurements will show up down here just below the edge, and then they can be moved up to wherever you want. And then they'll kind of stay where you put them. Okay? And so we can see that's the distance between those 2 points. As always, you can use the mouse to zoom in or zoom out or move around, move the plane around. Okay, and we can see that that's the midpoint, say by measuring the distance here and the distance here. So let's go ahead and show those labels here and here. And these labels are kind of dynamic, so that if I were to change this to the midpoint, say rename it M for midpoint, the labels are adjusted correctly. Okay, so there you go. There's the midpoint. You can see that these are those two distances are the same. No matter where I put them, they're the same as each other. Okay, so now let's see here. Okay, so if we have a line segment, then we can have a perpendicular. There's a unique perpendicular bisector. There it is. It is a line, of course, that goes through the midpoint, and it's a right angle here. So there's a tool for that. There's a tool for taking any line and take a point, well, let's say a point here that's on the line, and there's a tool that's supposed to do perpendicular to the point on the line. Now, if you look at the bottom of the screen, there's a little help down there. It tells you what order to select things. Select a point of intersection, then another point on the line. So we want it to go through this point and then say another point on the line is here. And so now, as this point is moved, it stays on the line. I'll pick the control point there. Let's try again. So let's say let's go through this one, another point. And I think this one will be free to move without changing the original. So all those are perpendicular there. Okay, in a similar manner, we can take a point not on the line here and do a perpendicular through that. That's also has a unique one of those. So this one, select the 2 points on the line and then the point not on the line this time. And so that stays perpendicular. And this should work, hopefully, even if these happen to be exactly the same x coordinate. We have the vertical option that should still create that for us. Now, let's see what else. So there's some perpendicular things. What else can we do? Well, we can deal with circles. Circles are interesting. We can do a circle by a center and a point. So notice that circles turn out to be Euclidean circles, but the center is a little bit lower than the center, the Euclidean center. The hyperbolic center is lower than the Euclidean center of this. Okay. I can also do a circle by center and radius. So I can give it a center and tell it to do a radius, say radius 1. And there is a circle of radius 1. Let's do another circle of radius 1. Okay, wait a minute, you think, look at that. Those don't look like they're the same size. Well, they are. They're exactly the same size. They're not the same size as Euclidean circles, but they are the same size as hyperbolic circles. So this kind of shows you that when it comes to measuring the distance, the radius here is 1 on both of these. Okay, so in other words, the distance from this center point to any point on the circle is 1 unit. And you can sort of see that you might say space becomes more dense as you get close to the edge there. You know, smaller Euclidean distances give you the same hyperbolic distance there, whereas up here it's much bigger. So it's a little a little bit different there in the way that operates. So things that have to do with distance operate quite a bit differently here. So you can also do things like this circumcircular arc still works. So just as there are 3 points on a circle, the 3 points will give you an arc of a Euclidean circle. Since these are Euclidean circles, the standard tool works fine for that. This also works for a Euclidean semicircle. Okay. All right, let's take a look at some other tools. I'm just kind of running through these tools very quickly. Okay, let's see. Next, we could talk about some angles. So here's a hyperbolic angle. It's going to be defined by 3 points there. So you want to click on a point on one ray, then the vertex, and then another point. Okay, maybe we'll show the labels for these guys. So A, B, and C. So this is angle B, or angle ABC, or angle CBA. We can measure that angle, clicking on the A, then the B, and then the C. And it calls it alpha, I think, in this case. Usually it defaults to some kind of Greek letter. And it marks it basically there for us. And it does measure it in radians, which is preferred. and it also measures it between 0 and pi radians. Okay, so if it ever makes a straight angle, it'll be pi. If it's the same rate twice, it has a measure of 0. And then we have, we can have acute angles, and somewhere in here there's a right angle and so forth. Okay, so you can measure angles like that. Let's see what else. We can have a hyperbolic angle of a specific measure. So we click on 2 points, a point, then the vertex, and then an angle. 45 degrees. Let's make a right angle. 90 degrees. Or I could have just typed in pi over 2, I think would work too. So there's a right angle. So let's look what happens when we measure that. I guess to measure it, I make a point on this one. Measure that angle. It does, when it has a perfect right angle, it will give the standard kind of right angle marking that we're used to. So we can create an angle of a specified size. All right, this standard reflect about a circle is a hyperbolic reflection. So it would be what would be reflecting about a line. If you choose the line as the mirror, this would be a line. It works the standard way. And a hyperbolic rotation can be done with this tool. And there's also so how do we measure angles? I've got a tool here that'll create a Euclidean tangent ray here and a Euclidean tangent ray here. So this model is what we would call conformal. It preserves Euclidean angle measurements. So how do you measure an angle? Well, you measure an angle between two, say, curved objects. In Euclidean, you measure the angle between their tangent lines, the angle formed by their tangent rays. So these Euclidean tangent rays, if we measure that angle, then we're measuring the angle between these two hyperbolic rays. So it's the same kind of a thing. Of course, I guess this is some kind of object in hyperbolic geometry because it's a set of points in the plane, but it's certainly not a line or part of a line. Okay, so that gives you a very quick overview of the tools. And so with these tools, you can explore all kinds of things in hyperbolic geometry, just like you would in Euclidean geometry. You can build triangles. Oh yeah, one more. Here, triangles are kind of an important thing in geometry. So I have a tool set up to where if you create two 3 points, you get a triangle. And let's go ahead and label these. And it goes ahead and figures out the lengths of the sides, and it's okay, it's supposed to measure the angles as well. I need to go back and fix that. It should measure the angles as well and figure out the defect. So we'll maybe talk about what the defect is later, but I'll fix that tool so it also shows the angles measured. So you can easily create a triangle real fast and measure all the sides and angles. All right, so that gives you a look at the tools that are available, and you can examine all kinds of things to see if certain properties about angles and triangles and sides and lines and whatever works, quadrilaterals. You can explore all of that in this environment just like you can in Euclidean geometry. And hopefully through studying this, not only will you study some cool geometry here, but you'll get a better understanding of what makes Euclidean geometry work. One final thing just to show you. I do want to show you this because I mentioned earlier that when you start with a line here, and you take a point that's not on the line, in Euclidean geometry, there's only one line through this point that's parallel to this line. Remember, parallel means that the two lines are in the same plane and they don't intersect. But I can show there are lots of lines through here. Here's one. Here's one. There's one. Here's another. Whoops, not that one. That one intersects. There's one basically just like that doesn't intersect. There's even a vertical line going through there. I can force that to be a vertical line. So there are actually infinitely many lines through this point which do not intersect the given line here. So here's the given line. Was blue, and the given point out here is here. There are infinitely many lines through that point which are parallel to this line, to the original line here. So that's the big difference between Euclidean geometry and hyperbolic geometry. Really, that postulate is the only one that's not the same. But with this new distance metric and this model, you can explore the consequences of that. Okay, happy exploring.